Hello everyone and welcome back to Math Made Easy. In our previous lectures, we started the topic of numerical differentiation and studied the forward difference formula for the first derivative. Today we are going to study another important formula as a central difference formula for the first derivative. The word central here is very important because unlike the forward or backward formula, we use points on both sides of the point where the derivative is required. We will derive the formula using the Taylor series and understand its order of accuracy and then solve the numerical examples stepwise. So let's just begin. So suppose we want to find the value of the derivative at x equals to xi. And if we have equally spaced data, we have points such as xi minus h, xi, and this xi plus h. So for the central difference formula, we use the function values as at xi minus h and xi plus h. So unlike the forward formula which looks ahead and the backward formula which looks behind, the central difference formula looks equally in the both direction. So that's why it is called as central difference formula. Now let's just derive the formula. So we start with the Taylor expansion of f of xi plus h about xi point. So that makes this f of xi plus h becomes f of xi plus h times f dash xi plus h square by 2 factorial f double dash xi plus h cube by 3 factorial f triple dash xi and up to so on. Now let's just expand this f of xi minus h. This becomes this f of xi minus h times f dash xi plus h square by 2 factorial f double dash xi minus h cube by 3 factorial f triple dash xi and up to so on. Now notice something very interesting. The signs of the odd order terms is actually changing. Now you just need to subtract the second expansion from the first one. So we have this f of xi plus h minus f of xi minus h, and on the right hand side this f of xi terms cancelled. And the second derivative terms also cancel. So what remains is this f of xi plus h minus f xi minus h becomes twice of h f dash xi plus twice of h cube by 3 factorial f triple dash xi plus up to so on. And therefore this f dash xi becomes f of xi plus h minus f of xi minus h divided by twice of h minus h square by 6 f triple dash xi. Now ignoring the higher order terms, we obtain this f dash xi is approximately equals to f of xi plus h minus f xi minus h divided by twice of h. And this is the central difference formula for the first derivative. Now look at the error for the forward difference formula. The truncation error was order of h. But look at the first neglected terms in our central difference formula as this minus h square by 6 f triple dash xi. Therefore, the truncation error becomes this order of h square. And so the central difference formula is become second order accurate. And this is an important examination point. So just remember this. For the forward differences, you have taken the truncation error as order of h, and for the central difference, we have taken the truncation error as order of h square. Therefore, for the same sufficiently small step size, the central difference formula generally gives you a more accurate approximation. Now let's just write the formula clearly. So for equally spaced data with spacing h, this f dash xi becomes approximately fi plus 1 minus fi minus 1 divided by twice of h. And this is the formula you should remember. The numerator uses the point ahead and the point behind the required point. And the denominator is basically twice of h. So be careful there. A very common mistake is to write this h instead of twice of h. Now the question is, when should we use this formula? So suppose our table looks like this is x0, x1, x2, x3 and x4. And if we need the derivative at an interior point, say x2, so we have the data available on the both sides as this x1, x2 and x3. So we can use the central difference formula. But if we need the derivative at the very first point x0, there is no x minus 1 available. Similarly, at the last point, there will be no xn plus 1. Therefore, the central difference is primarily used for the interior points only. Now we have a question here where we need to find this f dash 2 using the central difference formula from the given data as is x and fx values, where this x values is 1.9, 2 and 2.1 and fx values is 6.6859, 7.3891 and 8.662. Now first identify the point where the derivative is actually required. We need this f dash 2. So the spacing becomes this h equals to 2.1 minus 2. That becomes 0.1. Now uses f dash xi, which is approximately equals to f of xi plus h minus f of xi minus h divided by twice of h, and hence this f dash 2 approximately becomes this 1.4803 divided by 0.2, and therefore this f dash 2 becomes approximately 7.4015. So that's our numerical approximation. Now let's just understand what's happening geometrically. So the derivative of a point is actually representing the slope of the tangent at that point. But instead of using just one side of the point, the central difference formula uses 2 points as is xi minus h, comma f of xi minus h and xi plus h, comma f of xi plus h. So we are essentially estimating the slope using the information symmetrically distributed around xi. And that's why the central difference approximation is generally more accurate than the basic one-sided approximation. Now we have another example here where we have these values in the table as is x and fx, where x values are 0, 0.5, 1, 1.5 and 2, and fx values as 1, 1.6487, 2.7183, 4.4817 and 7.3891, and you need to estimate this value f dash 1 using the central difference formula. So we basically need this f dash 1. So the points immediately on the either side of 1 are this 0.5 and 1.5, and therefore this h becomes 0.5. And now using the central difference formula, this f dash 1 becomes is approximately f of 1.5 minus f of 0.5 divided by twice of 0.5, and then substituting it becomes is 4.4817 minus 1.6487 divided by 1, and that basically approximates to 2.8330. Now notice how simple the calculation becomes once we identify the 2 points surrounding the required points. So the basic central difference formula is actually second order accurate, but we can obtain an even more accurate approximation by including the additional terms. So this higher order central difference formula becomes this f dash xi approximately equals to f of xi minus twice of h minus 8 times f of xi minus h plus 8 times f of xi plus h minus f of xi plus twice of h divided by 12h, and with the truncation error as order of h to power 4, and with the truncation error is order of h power 4. Now notice that this formula uses 4 points around the required point. So we have now this basic central difference. So we have now for the basic central difference is this truncation error will be order of h square, and for the higher order central difference is order of h4 becomes your truncation error. So higher order generally means greater accuracy for the sufficient small h, assuming that this numerical data are sufficiently accurate. So that's all for today's lecture on the central difference formula for the first derivative. We derived the formula using the Taylor series for the f dash xi and learned that the basic central difference formula has an error of order h square, and we also discussed about the higher order formula with the order h power 4 and solved some numerical examples. So in the next lecture we will move on to the higher order derivatives, where will we see how numerical methods can be used to calculate the second derivatives and beyond it. So if this lecture helped you, please like the video and subscribe to Math Made Easy. Until next time, keep questioning, keep practicing, and I'll see you in the next lecture.